Right.
So let me just give a brief introduction. We are very happy to have Jorge Santos from the University of Cambridge telling us about AdS Euclidean wormholes. Take it away, Jorge.
All right, folks. So first of all, thank you all for showing up. I know that this is earlier than usual. I already apologize in advance. This coincides with the bedtime of my children. So if you hear screams, just plow through. I'll try to keep the show going on, even though it's going to be a bit hard. And finally, I would like to mention that this work was developed mainly in collaboration with Don Marolf. He should be here giving this talk. He would be giving a much better talk than I will. But unfortunately, he had other obligations. And I should also point out that there's some recent work that we've developed with Raghu, and you should also look at it, okay? It's not related with the talk per se that I'm going to give today, but it's also very interesting work with a slightly different perspective, again, on wormholes, but a particular type of wormholes, all right? So here is the menu for the day. So I'll start by giving a brief motivation. I think, I'll be preaching to the choir. Everybody here knows why wormholes are interesting. Even if you don't like them, I think they're fascinating objects. So I try not to spend too much time in the motivation. Then I'm going to tell you that there's a certain natural notion of stability that you can associate with Euclidean wormholes. I'm going to try to explain why some attempts that have been developed in the past cannot possibly work and why you have to do something different. And then I'm going to tell you about particular constructions of wormhole geometries, namely scalar wormholes, where we build wormholes out of some bottom-up type construction. And then I'll tell you about wormholes in actual string theory embeddings. I'll end up with some discussion and conclusions. And I'm afraid that the conclusions are not very conclusive. Okay, but that's good. That means there's loads of stuff to do in this area. So that's a great thing. All right. So it has long been known that S matrices and boundary correlators or boundary partition functions can fail to display the familiar factorization properties. I mean, the first person that I know that have to discuss this, it's ridiculous, but it's again back to Stephen in 87 and in 88. Just the fact that you can have topology change, for instance, allows you to have constructions that evolve into things that have baby universes, and that will seem to evolve naturally, things that start in a pure state into something that has a thermal state. So this is a bad idea if you allow, in particular, these wormholes to exist in the path integral. Or naively, it might appear like a bad idea, I should say. Okay. And people followed up on this. Coleman followed up on this in 88. And then there's amazing work by Steve Giddings and Annie Strominger in 88 and in 89. Okay. Now I should stress that this statement predates AdS-CFT. We're in 87, in 88, 10 years before AdS-CFT. And via causality, it also predates the new developments that we have in attempting to solve the black hole information paradox. I should say that this business of violence that we'll talk about now when we talk about the information paradox is independent of AdS-CFT, but it's certain, that AdS-CFT helps you drawing many conclusions about the information paradox. But his statement about wormholes were made long time ago. Okay, the fact that the presence of wormholes in the path integral can cause these failures has been observed long time ago. So I've been talking about wormholes. Some of you might already be opposing to this because you have not defined this, right? And I better define what I mean by wormhole. I'll try to keep my definition as general as possible. And here is one, okay? So these are connected geometries whose boundaries have more than one compact connected component. And these can be of any signature you want. It can be real geometries or it can be intrinsically complex. This definition will work for all of them, okay? Now, for the purposes of this talk, I'm going to try to be very simple and I'm going to keep the geometries real, okay? But you don't have to. And if you look at the work that I've recently developed with Raghu and Don, we consider geometries that we didn't cook them up. Steve Schenker, Saad, and Stanford cooked them up. But we also studied the stability there. But this is not the things that I'm interested in now. For the purposes of this talk, I'm going to try to keep everything real. All right. So even though all of these statements predate AdS-CFT, I'm going to try to use AdS-CFT to understand if wormholes are allowed in the path integral or not. So first I have to draw some sort of cartoon for the standard picture in AdS-CFT, okay? And if somebody pointed a gun at me and said, hey, draw to me a cartoon about AdS-CFT, and I didn't have much time to draw, this would be the thing that I would draw, all right? So I want to compute a partition function for certain special types of field theories. And how do I compute that partition function? Well, I consider a bulk path integral, here represented by this direction. This is the bulk direction. And at the boundary of this geometry that I have to find, I prescribe some boundary conditions that tell me how I turn on things in my CFT. And by computing this side, if you're very simple, it's just a gravitational theory, there's no string theory anywhere, then you compute this partition function in a specific limit of a certain types of quantum field theory, if you want to keep this channel. Now, this is not a setup I want to consider, okay? And I don't want to lie to you. I don't want to say, hey, we're going to consider AdS-CFT in its standard setup. That's not true. The setup that we want to consider is a little bit different. We want to not to compute the partition function. We want to compute, say, a partition function squared. And we want to follow our nose, right? So for each partition function, I should have one boundary. If I want to have the partition function squared, I should consider things that have two boundaries, okay? And if these field theories at each end here are truly independent, okay, from each other, then factorization properties of quantum mechanics tells you that the geometry should just be the product in the middle, should just be the product of two things that cap off smoothly, okay? Just two copies of these things that we have here, one for each boundary. They're independent from each other. They shouldn't talk with each other in any way. But you look at this and you think, wait a minute, I can certainly think of other types of geometries. I can think of geometries that fill in the bulk by connecting the two boundaries. Okay, so there are other types of geometry that can contribute to that partition, to the computation of that partition function. And because there are other types of geometries that can contribute, besides just the obvious product of the two, I'm going to represent the full contribution in this manner, okay, by this angle bracket notation. Of course, I'm anticipating that I'm going to choose, this angle bracket notation for a reason. There's a reason why I want this. But at this moment, it's just because it, to emphasize that it can be different. And here are the two candidate geometries. Maybe there's even more, okay? But these are two candidate geometries that I can envisage contribute to the path integral. So I have one boundary here, one boundary here. This is the one that I would have guessed, okay? But there's also this one here, and this is what we call a wormhole, something that connects the two boundaries, and they really talk with each other now, in some sense. All right? Good. So this represents a failure of factorization, because if you want z squared computed in this way, is not really the partition function squared. The partition function squared, in a way, would just be this guy. But now we get contributions that look like that, which means that z squared is not just z squared. And that's why we have this angle bracket notation, okay? Now, this seems to go against the familiar notions that we have in quantum mechanics, because there's failure of factorization. And so you might wonder how to fix this, okay? One possible resolution, and I'm not arguing in favor of it. I'm just saying it's one possible resolution for this, is that in fact, we have to change the rules of AdS-CFT. In fact, you thought you were computing some partition function for a single CFT, and it turns out that you are not. That's one possible interpretation. It turns out that you might be actually computing something that refers to an ensemble of boundary theories. And that's why we're actually using this notation. Okay, don't be naive about it. We're using this notation precisely because you want to refer to some sort of ensemble of boundary theories. That's one possible resolution. It's not the unique resolution, but it's one possible resolution. Now, let us imagine for a moment, assume that this correlator, which basically measures how different the z squared computed in this manner, where you include the wormholes, or just by looking at the product directly of these two partition functions, so this is a correlator that measures how different these things can be, is non-vanishing, okay? That is, imagine that this variance, if you want, is non-vanishing. What does this mean? Well, this delta z squared is just telling you how fluctuations of the partition function delta z are allowed to differ from the average, if you want, so this guy here, in a particular member of the ensemble. That's what this is measuring for you, if indeed the wormholes contribute, and there's only, say, one wormhole that contributes, okay? Now, this effective ensemble description can actually be derived, and it was first proposed by Coleman in '88, and then Giddings and Strominger put some more beef in it, but they made some assumptions, most notably the assumption of locality. And recently, Don Marolf and Henry Maxfield dropped that assumption, and they sort of derived the rules for assuming that indeed you have a bulk theory that is computing something about an ensemble of boundary theories. Now, let us assume that this is true. And again, I'm not saying that this is true, okay? I'm just saying let us assume that this is true. What are the implications? You really thought that you were computing something about a particular CFT, but it turns out that you might be computing something about an ensemble of CFTs. Well, this seems to be a little bit at odds with our usual interpretation of AdS-CFT, okay? Why? Well, most realizations of AdS-CFT involve bulk theories with large amounts of supersymmetry. And this supersymmetry should be reflected in each member of the boundary ensemble. So you must think, okay, in D = 4, how many, say, field theories can I find which have maximal supersymmetry, for instance? And naively, you'd say, well, there's only one, okay? That's n = 4 super Young Mills. And
sorry, George, can I ask a question at this point?
Yeah.
I mean,
sure.
in any idea of an ensemble, you're allowing yourself to deviate from the original theory, right?
Yep.
So what properties of the original theory are you insisting to keep? I mean, now you're insisting to keep supersymmetry, but you could imagine.
I think we have an argument in our paper, which I can't quite reproduce in top of my head right now, justifying why at least supersymmetry is very likely inherited by each member of the ensemble. But it's true that I don't know much more than that. I don't know much more than that. And I cannot quite recall now the argument that we give, but I think at least for supersymmetry, we're expecting each member of the ensemble to exhibit this supersymmetry. Well, I'm not so sure if you have a theorem for that, though. Yes, Edward?
Isn't that manifest simply because whatever you calculate in the bulk with supersymmetric boundary conditions is supersymmetric?
But why can't you have some, say, I don't know, emergent supersymmetry or something like that? Imagine that, I think that's what Eva is saying. Imagine that you average out and you get some effective supersymmetric description at the boundary for some reason.
Well, I'm just trying to understand what the rules are. You're letting yourself integrate over some other parameter which changes the theory.
Yeah, and it could be that supersymmetry is emergent, for instance. After you integrate out, you get something that is supersymmetric in the bulk.
And it should be evaluated by wormholes. I think the supersymmetry is a gauge symmetry in the bulk, right? So it should not be evaluated by wormholes. So it should be realized by each member of the ensemble. Well, only global symmetry in the bulk can be evaluated.
Yeah, I think that's true. I think that's true. But I should say that even this statement should have an asterisk here. Okay, should have something here. Okay, but because it could well be that that non-perturbatively there's actually many cases, many theories whose strict perturbative limit give you n = 4. Okay, and we cannot rule that out. It could well be that there's many non-perturbative completions, all of them supersymmetric, that as you take the weak coupling limit, strict weak coupling limit, just give you n = 4. They only differ from each other by non-perturbative effects, for instance. So it seems that we have two options. One that I understand Steve loves. There are precise cancellations when we add up all of the connected geometries with the disconnected boundaries such that the variance is 0, right? So let me give an example. Imagine that you have, I don't know, an infinite number of wormhole solutions. For instance, it can be much more complicated than this, okay? It could be even things that are not on shell. But imagine that you have an infinite number of wormhole solutions. Each of them contributes to that variance. You add them all up and you get 0, okay? That's one possibility I have nothing to say about. There's another possibility. Wormholes are forbidden in the path integral, full stop, okay? But if number 2 is correct, we should try to understand why, okay? If they're really forbidden, we should try to understand why. Understand whether something like 1 is valid, I think requires a lot more work, okay? It requires really understanding much more than what we know, say in particular string theory embeddings, for instance. So here is the question that I would like to address, and we were not the first ones to address this question. Are there stable Euclidean wormhole solutions with AdS boundary conditions? Okay. Well, we were not the first ones to look at this. There's probably even prior work to this one that I'm citing here. But Juan and Liat in 2004, they did some study. It's a rather comprehensive study, but I think it's fair to say that it's not conclusive, but Juan or Liat might just say it's not true. It's very conclusive. I don't think it's very conclusive. So some of the wormholes that they found were unstable. I'll tell you what I mean by instability. You should feel nervous. If I'm talking about Euclidean stuff, you should be looking at me like, what do you mean by stability? You know, there's no Cauchy problem for Euclidean stuff. And I'll tell you a little bit more in a little bit. The stability analysis was not complete for some of the examples, and some wormholes had no disconnected solution to compare with. Okay, so we want to find solutions with connected topology and solutions with disconnected topology so that we can compare not free energies, but can compare Euclidean actions to see which one dominates, for instance. There's some more recent work by this group of people here, Hertog, Trigen, and Van Riet, which argue that existent wormhole solutions are actually all plagued with negative modes. Okay, they're all unstable. Okay, so there was a gap in the literature here, right here. Can we find stable Euclidean wormholes with AdS boundary conditions and do a more complete, thorough analysis of the stability analysis of this solution? All right, so that's what we aim to do. Now, you should feel very nervous when I start talking about like stability of Euclidean solutions, particularly if you're in Cambridge, you start shouting at me, because the stability analysis is really a Cauchy problem. It really smells that you're talking about, some initial data. You perturb this initial data. You look at the future development of the initial data. Do you remain close to where you started? This is not the notion of stability analysis that I'm talking about here. The notion I'm talking about here is very different. It's the notion of negative modes, which I'm going to try to elaborate a little bit upon. I should say that, talking about negative modes per se would probably in itself be a whole seminar, particularly in the context of gravity, because there are many, many things that we don't understand about negative modes in the context of gravity. And I'm going to tell you a little bit about it, but this deserves probably a full seminar on this. Now, let's represent some Euclidean path integral collectively by something like this. You prescribe some boundary metric, here represented by G partial, and some collection of fields at the boundary with some boundary conditions. And it is your job or my job to compute this path integral. Okay, I've pulled out some factor of n squared here. This n squared here in principle might have nothing to do with SUN in the usual n equals 4 superring mills. In practice, when we're actually doing with a 5-dimensional example, it is, but at this moment it's just some number that I'm going to take to be very large. Okay, and it is my job to compute this path integral for you. Well, we're going to use the saddle point approximation, which might be a good idea or not a good idea to use. Depends if you want to consider off-shell solutions as well or not. We don't want to consider those. So if you take the saddle point approximation, take n to be very, very, very large, you can compute this path integral. Okay, it's not an exact result. It's only an approximate result. And you typically get two contributions. You get a contribution from evaluating the action on a saddle, okay? And then you get this one loop determinant that many of us like to ignore. Okay, so there's still a correction to this that has to do with fluctuations around the saddle point that we have considered, and many of us like to ignore this, all right? So how do you obtain this second order action here? Well, that's easy. You take your original action, Euclidean action that you started with, you expand to second order in the perturbations around the saddle point solution that you've considered, and this gives you this second order action, okay? Note that there's no first order action, and you should all know why. It's obvious. That's because you satisfy the classical equations of motion, so the first order perturbation is not there, okay? So there's only a second order perturbation. And now I can state what I mean by stability analysis. Stability analysis just amounts to the following: is this convergent or not? Okay, so if this S2 second order action is positive definite, then I can do this Gaussian integral, and I just get the correction to the result that I've obtained by evaluating it on shell. If it's not positive, then I have a problem. Okay, good. And right now, you should all be looking at me and thinking this guy is completely crazy. And perhaps you will still say that after my comment. Maybe it's something else. But for the case of pure gravity, it is obvious and known for a really, really long time that this quadratic action is actually completely unbounded from below. It can be as negative as you want, okay? And this is the so-called infamous conformal factor problem. Turns out that if you apply conformal transformations and you look at the scalar that represents these conformal transformations, it has the wrong kinetic term. It has the wrong sign for the kinetic term. And so you'll always have directions along the trace, for instance, of the perturbation that will lower the action as much as you want. Now you feel nervous about this. I still feel nervous about this. But Stephen and Gary, they didn't feel nervous about this. They said, okay, we see this with the wrong sign. Here's what we're going to do. We're going to perform a weak rotation on the conformal factor. We're going in a rather cavalier manner, just say wherever you see the conformal factor omega, let's weak rotate it, multiply it by a factor of I. And then everything that was diverging, there was an infinite number of negative directions, modes that were diverging, they all became convergent, all right? I find this a very cavalier thing to do because, in order to justify this properly, you would really have to understand the space of complex solutions, then in the end, choose the right contour of integration, and then do a saddle point on that contour of integration. And this is something that Raghu and Don and I had to do in the context of the double cone geometry. But here, we want to keep everything real. This is much more of an ad hoc thing to do. I should say that there are some papers in the literature in 2012 and more recently in 2020 that back up this procedure. These papers don't make a big deal about this, and I don't understand why. They do a field theory calculation that only matches the gravity calculation if you apply this weak rotation. And I think there's, that's really good evidence that this weak rotation is the right thing to do. However, there's a really big problem. I know that the conformal factor is problematic in the case of pure gravity, and that it's the only thing that is a priori problematic. As soon as you couple gravity to any form of matter, you're lost. You don't know which combinations of fields you have to rotate to get rid of this problem. You see, the conformal factor starts contaminating matter, and you don't know what is the weak rotation that you have to perform on the whole thing. And I stress this is a problem. Nobody knows how to solve this. Okay, take gravity coupled with a scalar. That's it. Nobody can tell me what exactly do I need to rotate in order to get rid of this problem, because the scalar degree of freedom that is encoded in this conformal factor is contaminating bits of the matter, and you no longer know which one you have to weak rotate.
Sorry, George, can I ask a question at this point? So this is reminding me of something that happens in kind of in the reverse. When you think about compactifications, there's a conformal factor in the internal space, and very naively, that's just blatantly unstable for the same reason that you're finding, that you're reviewing here. But there it's solved by the constraints of GR combined with the fact that there's generically a warp factor, it's a warped product that stabilizes that would-be instability. And here I wonder if it would have to do with the internal dimensions. I mean, when you do these AdS, CFT, Freund-Rubin solutions, they have large extra dimensions and large non-extra dimensions. And so if one of them varies over the other, could that
I love the way that you're thinking, but you immediately get into a problem with what you said. You see, you have to take into account also fluctuations of the free form, if you're, say, in 11-dimensional supergravity, and then you fall in this problem that nobody knows how to weak rotate these things in such a way that you identify which scalar you have to throw away. So
sorry, I wasn't sorry, I don't want to ruin your talk by going on too much about this, but what I was doing was not weak rotating. It was just a dynamical mechanism that stabilizes this thing in string compactifications.
I don't think this could possibly be the answer, because even just within pure gravity, just perturb the purely gravitational sector, and you already see this problem.
Okay.
Just the purely gravitational sector.
I mean, you have to solve, the thing is you have to solve all the equations, but yeah, you're probably right in this context. In the other context, it's very clear that without any wick rotation, what would have been a conformal mode instability is instead removed by solving another equation of motion.
But that shows that the first approximation that you did was not self-consistent.
Well, it's just that
we can
there's
show that in this case it is.
Yeah, it's just the other equation I'm talking about is a constraint, so you have to impose it. So it's probably different.
And it's true. You know, in this work where Gary Gibbons and Stephen Hawking identify, you know, this big rotation and that this does work, the constraints also play a role. Okay, so you know, they also play a role there, so they're not independent of that.
It seems to me the generalization of what Gibbons and Hawking did is just to make whatever mode by mode Wick rotation is needed so that the path integral makes sense.
You know, Edward, I love that idea. Let's keep with it for 1 minute, okay? Keep with me for 1 minute.
I can see the problem you're going to get in that 1 minute because we will define real instabilities.
Yeah. Let me just give me 1 minute, okay? I love that. I love that. So, but in order to do that, remember that first we need to understand it's true what you said. Let's rotate whatever we need in order to make this convergent and get rid of all problems in one go. I mean, there's an infinite number of negative modes, and with one rotation we get rid of all of them. So generically, this is really hard, right? You need to understand which ones are going negative and then show that you did the right thing, right? And generically, that's very hard. But keep with me for 1 second, okay?
Okay.
Okay. So instead, we're going to take a different route. It's actually a route that was proposed by Barak Cole long time ago in 2006. And you know, as with any work of Barak Cole, I mean, I really encourage you, every time he publishes a paper, just go through it, okay? Any work that he has done long time ago only becomes relevant ages afterwards, okay? I mean, he did this for, say, the large D limit of gravity, which is now a big industry. And, you know, he did it years ago before everybody else. And the same is true here. I think this formalism that he uses is just striking in order to understand perturbations, classical perturbations or off-shell perturbations of certain geometries. So what is the name of the game? Okay, so we look at this second order action, and it turns out that in many cases, this second order action can be written as a sum of two parts. There's a part which is non-dynamical. It's there because gravity has constraints, okay? And then there's a part which is dynamical. What I mean by non-dynamical, it means that this first part that appears here does not involve derivatives. Okay, it's just an algebraic thing, a Gaussian integral that you can just do. Okay, and then there's a bit which is dynamical. There's a bit that does involve derivatives. And it turns out that in many cases, it is this non-dynamical bit that has the wrong sign, for one of the variables. Okay, and what we're going to do is, okay, since this is the only guy that has the wrong sign, we're going to Wick rotate it and get on with it. This is very similar of what happens here. And so long as the metric admits this decomposition, you're in good shape. Okay, so you just Wick rotate this non-dynamical guy, perform the path integral, and reabsorb whatever you get into the measure. All right, so that's because we know that if you rotate this guy, at least this instability goes away. Identifying this decomposition can be very problematic, and in general, it's not even, you know, this doesn't happen in general. For particular cases, it does, but in general, it doesn't. For instance, it is a very big problem for those of you that are familiar with this to perturb higher dimensional black holes. Any of you that has studied perturbations of, say, rotating black holes in higher dimensions will know that this decoupling does not happen there. Okay, and that's why it's very hard to study those things, and you have to deal with PDEs and whatnot. But in many cases, this does happen. And because you just Wick rotate this guy, you get rid of this problem, okay? But you're not done. So we Wick rotate this alpha naught, which plays the role of the conformal factor. And then we just do the integral, all of these non-dynamical variables. After you do the integral, the Gaussian integral over these non-dynamical variables, you get a new action, a new effective action that only depends on the truly dynamical variables. At this point,
George.
Yeah.
Question. So does this also hold for your scalar example? Can we do that?
It does. Hooray, or else I would not be here giving this talk. I would be ashamed at home, curled up in a hole. Yeah, no, it does. Why it does? I have no idea, but it does, okay? And there are many examples where it doesn't. Thank you. So you get this dynamical bit.
Sorry,
yeah.
The conformal factor, doesn't it have derivatives also that are of the wrong sign?
You know, thank you so much for the question. For the situations where the background has enough symmetry, it doesn't. You see, all of the dependence with the wrong signs kind of goes into the angles. you'll see this playing right in front of your eyes when we get there. It will, I'll tell you exactly when it is. Okay, and if I don't answer your question, interrupt me, please. So at this stage, we introduce gauge invariant variables. Until now, this was valid for a generic decomposition, and now we introduce gauge invariant variables. You want to make a statement that is gauge invariant. So in fact, you left with studying a quadratic action that is a function of a much smaller number of variables than the ones that you started with. And then you study the sign of this, and hopefully you're happy with it. Okay. Now, is it that simple? It looks so simple. There's a decomposition. You do the Gaussian integral over the other guys, then you're left with this quadratic action. You're done. Well, not quite like that. As I emphasized before, probably too much, this decomposition into a bit that is non-dynamical and the bit that is dynamical doesn't always happen. Most notably for perturbations of rotating black holes, it does not happen. And right now you should be asking yourself, how do people do Kerr, study perturbations of Kerr? And I'm not going to tell you. It's using something completely different. It is also not guaranteed that you can find gauge invariant quantities. That's another problem. In general, you cannot. Okay, but if your background has enough symmetry so that you can reduce everything to studying ODEs, that's the crux. Then you're good. You're good to go. Good. And even when you can do all of this, okay, it is a daunting task to study the positivity of this object. Our paper on this that Don and I wrote has some 80 pages or whatever it is. 80% of that paper is to study positivities of these things, of these factors. It's just really, really hard. And you might think that I'm a bit dumb, but remember, Don is in the paper and he could not tell whether those things were positive. It's just really, really hard in general to check that those things are positive. And in fact, sometimes they're not, and you will see them playing in your face. All right, so we've studied all the examples that I'm going to show you. We actually studied the stability in this sense, checked whether negative modes existed or not. I'm not now going to try to convince you that what people have done in the past, with some honorable exceptions, could not possibly work, okay? In order to find solutions that have wormholes. First, I should remind you that Edward and Yao have proved that at least in the context of gravity, just pure gravity, you're not going to find wormholes unless you have a boundary metric that has a lot of negative curvature, okay? But those boundary metrics that have a lot of negative curvature, they will obviously have other pathologies, which I'm going to discuss towards the end. So we don't want that, okay? We know that we have to include some form of matter. So you're going to start with the Einstein equation coupled to some matter with the bulk stress energy tensor, TAB. This is the bulk guy, okay? This is not the holographic stress energy tensor, just some bulk matter, arbitrary bulk matter for now. We're simple dudes, so we're going to take a homogeneous and isotropic FRW type ansatz, okay? So here, this ds squared is some d-dimensional sphere, for instance, or Euclidean space, or the hyperbolic plane. The hyperbolic has negative curvature, and there we know that we'll be able to find wormholes, but for completeness, we leave it here. Well, we look at the Friedman equation, or the Euclidean Friedman equation, which is the equation that follows by looking at the constraints. So these are tau component of the Einstein equation. And this is what you get, where this rho here is just the usual Lorentzian energy density. Okay, the usual thing that you would write down. So this is looking rather good. Okay, for a wormhole to exist with AdS boundaries, if you look here, you need A to go to infinity as you approach the boundary. We're interested in two boundaries. We're going to put one at tau equals plus infinity, another one at minus infinity. So A needs to blow up there. But if A blows up at those 2 points, it will have a minimum somewhere. Okay, so A dot will vanish. And indeed, looking here, it seems that we're in good shape. There's loads of matter with positive energy density. So maybe we'll find a zero, okay? And we'll have a wormhole solution. So this is looking rather good. Thumbs up. We're enjoying this so far. Note immediately that if you have spheres that corresponds to this k being equal to 1, you need to cross a certain threshold here. The energy density needs to cross a certain threshold in order for you to have a zero there. So it kind of suggests that if you have a spherical boundary, that you need to have an energy density that is bigger than a certain number in order to have some sort of existent wormhole solutions. Now, here's the problem. Since we want to satisfy the AdS boundary conditions, we want to impose some sort of matter that is gravitationally attractive in Lorentzian signature, right? We want gravity is sort of more attractive in AdS. Once you Euclideanize this in Euclidean signature, this turns into gravitational repulsion. And you would feel tempted to say, aha, I'm going to use tau derivatives at the minimum to create this gravitational repulsion and thus open a wormhole. Okay, you'd be very tempted to do this. And in fact, people have done this, many, many times. They use axionic matter to do exactly this. The problem is that this would imply imaginary derivatives for a Lorentz signature field. And this is the reason why all the examples that people have worked out in the past, with the exception of the ones by Juan and Liat, have negative modes. These axionic sourced wormholes all have negative modes because of this. Okay, we can track this down to this. So you cannot use these tau derivatives. That's out of question. So what do we do? Well, we will use spatial gradients to do the job. Okay, and you immediately think, aha, that's why George is in this project, because if it involves spatial gradients, we'll need to solve some sort of PDE. But I was very lazy in this project. We don't need to solve any PDE. It turns out there's loads of tricks where you can only need to solve ODEs. It's as simple as it gets, okay? And I'm going to try to convince you of that. So for the first time now, I'm going to tell you about the solutions that we actually constructed, tell you how wormholes look like, okay? So I have to specify first the theory. I'll start with a simple theory. Well, I guess simplicity depends on the eyes of the beholder. It's a bit like love. So this is a completely ad hoc action. Here it is. What are the ingredients in this action? Well, we'll have gravity here, a negative cosmological constant, and then we have a doublet of complex scalar fields. So this guy has two entries. It's complex. It's like a vector, and each of these components is complex. Okay. We're interested, in our paper, we study many other cases, but for the purposes of this talk, we're interested in boundary metrics, which are spherical. And for now, I'm going to give you a 4-dimensional example. So the boundary is 3-dimensional. So I want the boundary to have an S3, a round S3, okay, round 3 sphere. And this is the boundary metric for a round 3 sphere. And some of you might be thinking, what the hell are these sigma 1s? If you're in Cambridge, this is your bread and butter. You have to know this in part 3. Gary Gibbons loved these things. These are just left invariant one forms on the S3, and it turns out you can write the round S3 in this manner, where these sigma 1s satisfy these beautiful Morocarta relations, which are very, very useful. Good. Remember that you have to supplement your action by introducing some sort of boundary term so that your variational principle is completely well-defined. There's 2 types of boundary terms that you need to introduce. You have to introduce the usual Gibbons-Hawking-York boundary term. Probably only in Cambridge we refer to this Chap-York. And don't forget that you also need to introduce boundary terms that are related with the actual matter, okay? And depending on the value of mu, there will be different boundary terms that you need to add. Now, I just told you that Edward and Yao told us that you cannot do this just with pure gravity without making the boundary metric negatively curved. So we need to turn on sources. We need to kind of source these wormholes to open up. So it is not a surprise that we're going to take these scalars here to have a non-zero source at the boundary. And we want to make this source large enough so that we can open wormholes in the bulk. Now, I promised you that we could do this with ODEs, but at the same time, we want to use spatial gradients, okay? So how on earth are we going to do this? When just ODEs, but at the same time, spatial gradients. Some of you already know immediately what I'm going to do, because you look here and you see, aha, there's a complex scalar field here. So you're going to use the fact that it's complex scalar and give definite phases so that the dependence in the angles all cancels out. And that's exactly what I'm going to do. Okay, this is a setup that Gary Horowitz, Oshkar Diaz, and I have used a long time ago to construct black holes with a single killing field in AdS. So what do? You take this complex scalar field, doublet, pi. We say it's equal to some vector. This vector is a complex vector. It's non-zero. Its gradient is also non-zero. And it's such that it squares to 1. Okay, we're going to take this scalar field pi to be such that when you go to the boundary of AdS, you get a number which is real. And that's the number that we're going to dial to try to open the wormhole. Okay, is this clear so far? So this is a trick. All the dependence in the angles is inside here. Okay, in this vector. Now, why is this useful? Because we chose this type of matter, it turns out that our stress energy tensor resulting from choosing this is spherically symmetric, even though the matter field is not Okay, the metric field is not because there's this dependence on the angle, but because this vector satisfies these beautiful relations here. It turns out that the stress energy tensor is spherically symmetric. For those of you that do AdS-CMT, I'm not so sure if there's many of you here that do, this is very similar to something that's called a Q lattice. For those of you that do GR, this is very similar to something called a boson star. Okay, but we do it in this context. So the dependence in the angle and the spatial momentum is all encoded in this vector here. And this turns out to be a particular mode on the sphere. It's just an L equals 1 on the 3-sphere mode in terms of spherical harmonics. All right, what about the metric? Well, we cook this up in such a way that the metric is still spherically symmetric. So the metric just depends on these two factors, G of R and F of R here. So what happens, for instance, for pure AdS? For pure AdS, F of R is just equal to this factor, R squared over L squared plus 1. And this G of R is just equal to R squared. And R for pure AdS, global AdS, varies between 0 and plus infinity. So how do you distinguish between wormholes, okay, and disconnected solutions, solutions that cap off smoothly? Well, they are distinguished by what G of R does as you move inside the bulk, okay? So the wormhole solutions will have a G here, the sphere will not close anywhere. That's a wormhole solution. And the disconnected solution will be such that G of 0 is identically 0 at R equal to 0. So if you follow your notes, just plot the radius as a function of R, you should see a plot like this for the disconnected solution. So G of R vanishes here smoothly so that you have no singularity. And for the case of the wormhole, it doesn't, okay? And in fact, there's a certain inheritance of symmetry because we want this boundary to be exactly equal to that so that there's no interaction between the two. It actually ends up being Z2 symmetric. Now, some results, okay? Finally, I get to the results. Here it is. So we've considered two simple examples for the case of the scalar in the action that we just given, the massless case and the conformally coupled case. For the conformally coupled case, the mass squared is -2. Remember, the mass squared can be negative. We all know that. For the massless case, it's 0. Okay. You might wonder why we consider both examples. Well, it's because Juan told us. Juan told us, well, you find this for the massless case, but you won't be able to find it for the conformal case. And we wanted to show that this time Juan's intuition might have been wrong. And I think we managed to do that, but we'll see. So let y naught be the minimal value of the radius of the S3 in the whole of the manifold. So this is the value of the radius at this plane of symmetry here, okay? That y naught be that minimal value. As expected, because the boundary metric is spherical, wormholes only exist for a value of V of the source above a certain critical value, V minim, okay? That value strongly depends on the mass. And in a certain sense, Juan was completely spot on. I mean, as usual, okay? Look, this is the amplitude that we need in order to open a wormhole case for the case where you have 0 mass. So massless case, 3.38. But look, because we wanted to show that Juan was wrong, look at the value that we got for mu squared L squared equals -2. 179 is much harder to open a wormhole with a conformally coupled case. Much, much, much harder, okay? So his intuition was spot on, as usual. So what am I showing here? I'm showing the minimum value of the neck, if you want, of the wormhole as a function of the amplitude, as a function of the size of the source at the boundary. What is the first surprise? Well, the first surprise, perhaps a surprise, is for each value of the source, I find 2 wormhole solutions. This is double the work for the same amount of, double the results for the same amount of work. For the one value of V, I find a small wormhole solution and a large wormhole solution. I think it's obvious why I call one large and the other one small, because one, well, actually has a larger neck than the other for a fixed amplitude of the source. Okay. On this side, I have mu squared equals to 0. On this side, I have the conformally coupled case. And in both cases, I need to go sufficiently large V, sufficiently large source in order to see the wormhole opening up. Okay, good. I will try to keep this color code. Things that represent small wormholes will be represented by orange squares, and things that are large wormholes will be represented by blue disks. Okay. We also find disconnected solutions for any value of V. For any value of V, we can construct also numerically some disconnected solutions. Okay. So one thing that we should check is which one dominates the ensemble. We evaluate the on-shell action, okay, for the disconnected solution. We multiply it by 2, y by 2, because we're considering two boundaries. And we compare that with the on-shell action of just having a single wormhole, okay? Which one is lower? The one that is lowest will dominate, at least naively, the ensemble, so long as there's no negative modes. This is what we find. So delta S here is just twice the action for the disconnected solution. There's two boundaries, that's why you need a factor of 2, minus the on-shell action associated with the wormhole solution, okay? And what we find—
Sorry, George.
Yeah.
What's the units of the V?
It depends. So this case is the massless case. Thank you for the question. This case is the massless case. So there's no units on this. This is just a marginal deformation. In this case here, it's in units of L. So that's in units of the boundary of the radius of the boundary metric.
Even for masses, you are considered higher dimension. So the, the scalar also have mass units, right?
Yes. No, but for the massless case, so this is literally just this. Look, V plus blah, 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 blah. And this is this number. For this case here, it's different. So for this case, it is something like Z to the 1. And this is the number that I'm plotting here. And because, you know, so this is ultimately all divided by L, which is the radius of the boundary metric, related to the radius of the boundary metric that I'm considering.
Okay.
So,
thank you.
Yeah. So what is interesting is that if V is large enough here, we find that there is a Hawking page transition, that the wormhole solution wins. The wormhole has lower free, sorry, no, I keep saying free energy, lower on-shell action. The same is true here, okay? Even for the conformally coupled case, we have to go to much larger amplitude, but it's still true. We go to sufficiently large amplitude, okay? And the wormhole solution has lower on-shell action. So it seems to dominate the ensemble. Well, what about the study of the negative modes, okay? I'm going to be very terse here because I don't want to spend 80 slides explaining what we had to do, okay? So this is the most complicated part of the paper, and I encourage you to somehow skim through that, okay? So we also studied the existence of these field-theoretic negative modes, okay? This might look completely hopeless, okay? But remember that the metric has spherical symmetry. And because the metric has spherical symmetry, we can decompose everything in terms of spherical harmonics on the S3. So you'd think that you would have to deal with PDEs, but we don't, because we expand everything in terms of spherical harmonics. We are only left with, ultimately, only with ODEs, okay? And because we're only left with ODEs, it's very easy to identify which mode is the equivalent of the trace mode and which mode is the equivalent of the truly dynamical modes. And this is where I can answer to one. After you apply this harmonic decomposition here, the equivalent of the trace mode is purely algebraic, okay? If you did not apply this decomposition here, this non-local decomposition in terms of spherical harmonics, then you'd have derivatives with respect to the angles. So if you want the factors of L, there's like L plus 2 or whatever it is, all come with their own sign. Now, large wormholes are free of negative modes. They have no negative modes. We've searched many, we can see the details in the text. In fact, for this case, we can actually prove that there's none. But small wormholes have at least one negative mode, at least one. And just to show you that I'm not lying, here is the minimal radius of the S3 divided by Y0 minim. So this is the value that Y0, the radius of the S3 in the bulk at the Z2 symmetry plane, has at when the wormholes just start showing up. And you see that the small wormhole branch, which is this guy, always has a negative mode. This is the negative mode. And when you cross 1, they no longer have a negative mode. This is highly reminiscent of what? Okay, think about Schwarzschild AdS. If you think about Schwarzschild AdS, it turns out that people have studied the negative mode of the Schwarzschild AdS black hole. You know, it's a very Cambridge thing to do. If your PhD is stuck, one of the things that you do is you study a negative mode of some geometry, okay? I've been there, okay? I've done that. And Prestige in 1999 studied the negative mode of the Schwarzschild AdS black hole as a function of D. And the specific hit is related with the existence of this negative mode, as was envisaged a long time ago by Yaffe and collaborators. So in fact, in this range, the usual Schwarzschild AdS Euclidean Schwarzschild AdS black hole has a negative mode. But note that this is always below the Hawking page transition. The Hawking page transition occurs when R plus over L is bigger than 1 for black holes that are sufficiently large, which is always bigger than this value. So what I'm going to do now is to plot side by side the phase diagram for Schwarzschild AdS compared with the phase diagram for our wormhole solutions. I mean, isn't this striking? The only difference is that I'm putting here the temperature. That's the source, okay, for the case of the Schwarzschild AdS black hole. And here I'm putting the actual source for the massless case. Look at this. It's very, very similar. Negative mode here, negative mode here. Hawking page transition after the negative mode, Hawking page transition after the negative mode. I mean, remove the numbers here and you wouldn't be able to tell which one is which. I still find this striking, but perhaps I'm alone in this. So this is a case where I decided to cook up some action that I pull out of the bag and it was useful, okay? Well, but string theory doesn't allow you to do that monkey around with the action. The action is fixed for you. You go to some, 11-dimensional supergravity or type 2A, and you start there, you reduce it down to lower dimensions, you get what you get, and you have no freedom in doing more than what you get, okay? So we decided, all right, let's do this. We've understood about a dozen bottom-up models. So a dozen examples of the sort we've done before with different matters, different boundary metrics. We always got the same picture. So we decided, all right, let's study examples in string theory. There's a nice thing in string theory. String theory has other instabilities. It turns out that you also have brane-nucleation instabilities. It might be that branes want to nucleate in your geometry. And if they want to nucleate in your geometry, well, that's no longer a saddle. Now you need to include the branes and check the new saddle. Okay, what happens now? Well, these instabilities will tell you whether branes, it's actually a pair of brane and anti-brane, want to spontaneously nucleate into your wormhole geometry or not. And if they do, there will be a new phase with a lower action. It's not necessarily an instability in the sense that we've seen before, because these branes are quantized, so it's not quite an instability, but it still points to the existence of some solution out there which has a lower Euclidean action. Which probranes you consider? Well, that depends on which embedding you consider. If it's in type 2A, you have to consider some types of branes. Type 2B, some other branes. In 11-dimensional supergravity, you consider some others. So it depends on the field constant. Okay. Here we shall report only on the simplest example, okay, which is an embedding in 11-dimensional supergravity. So here is the bosonic action for 11-dimensional supergravity. There's a pesky factor of I there. It has to be there. Think about it. We're working in Euclidean signature. That I has to be there. There's nothing you can do. And here is a simple, and I quote simple because people study loads of consistent truncations. And trust me, this is what they call a simple truncation. In my dictionary, I wouldn't call this a simple truncation. This is complicated enough for me. But this is what they call a simple one. So this is the 11-dimensional metric, okay, here in its full glory. And this is the 4-form field strength, okay? All I want you to know is that there are two Maxwell fields here, F1 and F2, which only live in 4 dimensions. And it turns out that if you take this horrible ansatz into the equations of motion that come from 11-dimensional supergravity, you get some 4-dimensional equations, which can be deduced purely from this action. So the idea is you take the ansatz that you've seen before, you get some 4-dimensional equations of motion. It's not obvious that you're going to get them, but you get them. And then you realize that those equations of motion derive from this action. You should never do this at the level of the action, okay? Always at the level of the equations of motion. This is a very familiar action, right? 2 Maxwell fields, negative cosmological constant, very familiar action. It's like Einstein-Maxwell double. What are the ingredients? Well, you can guess. We're still considering a round sphere, okay? Here is just the Gibbons-Hawking term. You might think there might be another term associated with the gauge field. There aren't any, and you should read a paper by Stephen on this, why there's nothing else that you should add there. And we are interested in source solutions for which the boundary value of these Maxwell fields are non-zero, okay? And now I'm not going to bother you with the technicalities, but we have 2 Maxwell fields, and you're going to align each of them with these left invariant one form so that you're still left with ODEs. I'm not going to bother you with this. Okay. Again, there's only one parameter, deformations, which is just parameterized by the amplitude of this overall factor here. Okay. These solutions are no longer spherically symmetric in the bulk. All right, but the resulting things are still homogeneity 1. And if you want to know why, just look into the literature of type 9 Bianchi spacetimes. It falls into one of those classes. We repeated the exact same analysis. Wormholes exist. Hooray! You should all be happy. Okay. Well, for sufficiently big source, it turns out that large and small wormholes exist, not just one type. Again, we have 2. And again, for sufficiently large amplitude, the wormholes become the dominant solutions. They have lower Euclidean action. So it seems that we're all going in good shape. And here is the plot. Look, it's very similar to what we've seen before, right? We all agree that this is very similar to the plots we've seen before. This is the value of the source. This is just the minimal radius. This is the action. And again, we see a Hawking page transition. What about the new instabilities? The new instabilities that have to do with the brane content that only string theory could give you, nothing else, okay? Well, things become very, very interesting when you include those instabilities. It turns out that most of the large branch here is unstable to the nucleation of branes, okay? So branes, if you include these string theory objects and study whether you form an instability or not, it turns out they do. They do, and they want to destroy your beloved wormholes that you constructed with so much sweat, okay? Now, they don't destroy all of them. Look here, there's a corner here where the wormholes still exist, but they're subdominant, but the branes don't want to destroy them. Furthermore, we also studied the negative modes. It's very hard to study the negative modes of this one. You should know why. It's because the solution is no longer spherical. So you have to use some other harmonic decomposition in terms of some other functions. Okay, these functions that live in U2, and they're very well known, and you can use them. It's harder, but there's no negative modes there in this corner. It's subdominant. So it seems that string theory, the content, like the field content, I find this extraordinary. The field content of string theory wants to destroy our beautiful wormholes, wants to make them subdominant. Okay. We have no idea why that's the case. All right, so I'll now come to the discussion and conclusions. So we have repeated this analysis, exactly similar to this one, for 22 string theory or M theory compactifications. That's quite a bit of them. And the results are all similar, okay? First, the dominant wormholes, when they exist, always seem to have brane-nucleation instabilities. That seems to be just a given. And this matches very well with what Juan and Liat saw. In some of the examples that they studied, they see this. They see brane-nucleation instabilities whenever the wormholes exist. Other examples are even more interesting. It seems that you have everything for this to work. Okay, you're like, okay, this is not going to get brane-nucleation instability, but it turns out that the potential, just the potential that comes from string theory actually do not allow for this, do not allow for these wormholes. There's some funny potential, some cosh of the field that shows up that kills the wormhole solutions. We have worked across several dimensions, 2, 3, 4, 5, and 6. Okay, and the pictures are always very similar. In fact, just like the BTZ black hole only has a large branch, it turns out that in 3 dimensions, the examples we constructed, the wormholes also only have a large branch. Okay, we consider toroidal boundaries and top and down approaches and in bottom up, and it's very, very similar. All the examples that we have worked out have a conserved global charge. So this is to make the analysis simpler so that we get ODEs, but it's a fact, okay? We're now trying to do this for true PDEs. We consider boundary metrics which have less symmetry. For instance, the squash test 3 is something that is easy to consider. And again, the results are very, very similar. What does this all mean? And this is the bit where, this is completely, this is not necessarily true. This is just our interpretation of the facts, okay? So we believe that our results are natural, even if one believes that bulk AdS gravity in some UV complete theory is actually describing an ensemble of quantum theories, okay? Why do we believe that this is still true, or that this could be seen as evidence in favor of this, okay? Doesn't have to, but could be seen as evidence in favor of this. Let us imagine that we found that the wormhole solution dominated the computation of the partition function, okay? this would have implied that the ensemble fluctuations of the partition function were very, very large, that this variance that we defined initially would be very, very large. But this is not what's seen in lower dimensional examples. In lower dimensional examples, where we can actually compute pretty much everything, it turns out that everything is actually very narrowly peaked, okay, around the average. So this would contradict somehow what is seen in the lower dimensional examples, where we can dot the i's and cross the t's. So what are then the implications of our subdominant wormhole saddles in string theory compactifications? Okay, remember that we still found a region where the wormholes were fine and dandy. Well, it is generically a bad idea to draw conclusions from some dominant saddles. We all believe that's the case, unless you find a quantity that vanishes identically, okay, on all dominant saddles, and you're left with something that is a non-zero. We do this all the time at LHC, right? We find sometimes some phenomena that only is non-trivial at the loop level, which is a great way to test physics at the loop level, because this quantity would only be different at the one loop level. Here is the same thing, because for all connected solutions, this variance is identically zero. So the fact that we see a region there where the wormholes are subdominant but seem free of pathologies, well, could be problematic for the factorizations. It doesn't have to be. It doesn't have to be, because you can have a whole slew of things that you have to add up, and after you add them all up, you still recover perfect factorization. Okay. So again, unless such contributions fully cancel amongst themselves, this is suggesting or giving some meat, if you want, in favor of this picture related to the ensemble average of quantum theories. So the factorization problem of AdS-CFT seems to remain far from resolved, and will be surely object of much future investigation. I hope I'm involved in such investigations, and I would like to thank you for your time. And sorry that I've already overrun for 5 minutes.
Let's thank George for an amazing talk. Thanks, George.
Thanks, George.
Yeah, we have time for some questions. The floor is open. Just please unmute yourselves and ask.
When you increase the source so that the two solutions appear,
Yes.
when that happens, when they appear, they're born fully non-singular, even at threshold, aren't they?
Yeah.
So that actually implies that one has to be unstable, because you're varying a function whose critical point you're looking for. When two critical points appear, if one is local norm, the other can't be. It's a saddle point.
Yeah, true. It's a catastrophe theory, right? You have two things that are meeting there at a point. There has to be a zero mode. That's what you're saying. You're varying the parameter a little bit and nothing in varying, so there has to be a zero mode. We use this all the time in black hole perturbation theory, all the time. All the time. Yeah, and in studying the stability of neutron stars as well, all the time, the same thing. So it is obvious that some stability analysis would have to show up there and indicate the existence of a negative mode. And indeed it does, because the small wormhole solutions all have a negative mode, just like for Schwarzschild AdS. For Schwarzschild AdS, if you do exactly the same plot as a function of the temperature, it's also true that the small wormhole, the small Schwarzschild AdS branch will have a negative mode. So you're right, the stability changes.
So George, just trying to make sure I understood correctly. So in these scalar plus the gravity case that you considered, the conformal factor problem didn't show up because you had enough background symmetry? Was that what you said?
So,
okay.
Yeah, so you have enough background symmetry so that you can identify what would be the problematic mode. And then, which is indeed a funny combination of the metric and scalar. And you weak rotate that and you're done with it. You're left.
You do have a negative mode, but it's sort of identifiable because of the symmetry.
Yeah, exactly. You're lucky.
Just
Nothing
a
else.
very naive question.
Yeah.
In general, why would negative modes be so bad? Like, I could imagine if you were trying to compute a real thing and you had an odd number of negative modes, that would be bad. But what if you have an even number?
another great question, and it's indeed not obvious. It's indeed not obvious. What I think is guaranteed to be bad is if you have an infinite number of them. I think that doesn't smell right if you have an infinite number of them. But if you also have an infinite number of them, and it turns out that with the right weak rotation you get rid of all of them, then you'd feel comfortable with. The problem is that sometimes you weak rotate the field to get rid of what you think is one of them, and you end up getting rid. You end up getting rid of an infinite tower, but creating a problem somewhere else. But I agree with you. When there's more than one negative mode, it would seem to me still that the path integral, if you just keep everything real, is poorly defined because you're sitting at the saddle. So when you're going to integrate and compute the one loop determinant, you're going to find a problem. But in the Lorentzian section, I think that's your question. Is less clear.
Like no, I meant in Euclidean. Like it seems like the question is whether you're supposed to include the saddle or not, and that's a hard question to answer. But if you somehow know that you are, then you can do the integral in some way that makes sense.
I mean, that integral, strictly speaking, is divergent, right?
Yeah, but well, there's some contour for which it's convergent.
Yeah. I agree. I don't disagree with that. I don't disagree with that. I don't disagree with what you just said. And in fact, in this other paper that me and Raghu and Don wrote, yes, you have to study the path of steepest descent. It's not just like what you're saying, right? You first need to find the path of steepest descent in which you can deform the contour. And then on that path of steepest descent, you take the saddle point approximation, and then you compute whatever you want to compute. But first you need to find a path of steepest descent. It's not just weak rotating and get it done with it, right?
Well, yeah, that's if you want to really justify whether you should include that saddle point. But if you just say, okay, I should include it because I don't know why, I just think I should, then it's not so hard. You just basically do the integral over the convergent contour starting at that point.
But would you be okay if the contour dependent on which mode you're looking at?
Yeah. So that's
okay with that.
Kind of what I'm asking. Is there some
I would not be okay with that. Imagine that you're doing an harmonic decomposition in terms of spherical harmonics, and now you label all of these perturbations by L. And if you fix L bigger than 20, you end up creating negative modes for L smaller than 20. So whatever weak rotation you do, it would depend on the value of L. I find that weird, but you might say it's not. And until somebody goes and comes and justifies, it is what it is.
Yeah. Okay. Thank you.
I should just one thing that I did not mention, but it turns out that many of these things in certain cases can be done analytically. Okay. So I've shown you the example of the scalar fields, but it turns out that if you allow yourself 3 Maxwell fields, and if there's no other scales around, you can actually find these wormhole solutions completely analytically and study their stability, and the picture is exactly the same. But they don't descend from any string theory compactification that we know of.
I have one other, this is kind of a stupid question, but like you discussed all these cases, right? These 22 different compactifications and like different dimensions. And so you said that in these cases, anytime you found a large wormhole that was dominating, it was unstable to brane-nucleation. Do you have any sense of like how surprising this is given the ingredients that went into the calculation? Like, is there something special going on that's making this true, or was it kind of
I don't know. It really seems to, we thought a lot about it, and in a certain sense, we had these results since March 2000 and even earlier. I think I was already telling Edward this even longer than that about some of these results. But the problem is that we couldn't find any general argument. And it really seems to depend, there are examples that are even more awkward, okay? It seems that you have all the ingredients. You have 3 complex scalars, or 4, say, complex scalars. And, you know that you're not going to have any brane instabilities. But the potential, the potential is not, it's not a massless field that will necessarily come. It will come with some interactions. The potential kills you. Like the form of the potential just kills you, okay? And once I started seeing these type of examples, I started becoming much more worried if it was something that was not easy to guess. Arguably, I'm not the most creative person, so maybe somebody else will find a generic argument, but it cannot be something, I think, very simple. It cannot be something like positivity of energy or something like that. I think it has to be something different. So I don't know how to answer your question. I think it's interesting that it seems that it's string theory. I'm saying that these branes only exist there. That seems to give you an expectation similar to what you see in lower dimensions. And I think that's interesting. And in the back of my mind, this is saying that maybe there's some evidence for this picture with an ensemble average. What? I mean, if it is like what you said in your last paper, that you should include things that are not saddles and these half wormholes, and if they all ended up canceling against this, then it is what it is.
So I have a very naive question. Just trying to understand this function delta z, the difference of the partition five. I mean, if it factorized or not. On I think it was on your slide number 5 where you were trying to compute it on AdS2 space, which was basically this cylinder, and the two CFTs were living on the boundary circles.
No. You should. These are just pictures. Okay. There's nothing here in AdS2. Okay. These are just slide number 5. You're saying these are just pictures.
Yes. That's weird. Sorry.
Yes.
Well, okay,
Here.
that thing is there. So
these pictures,
and
these are just
exactly.
pictures. These are, you should regard these as higher dimensional things. It's just
no, that's okay. That's okay. But it's so this difference is, if I mean, it should be a function. It should be some geometric property on the space of geometries of such things. So for example, I mean, just because this picture is low dimensional and one can say something, in this case, it seems that there is one unique minimal length geodesic on this cylinder, the one in the middle. And is this difference function somehow related to that, the length of that geodesic somehow? Or let me just ask it more vaguely. Do you have a geometric interpretation of this difference function as a function on the space of geometries of such wormholes?
I mean, all I can tell you is evaluate the on-shell action, right? One will give you delta z squared. The other one will give you the other quantity, and you subtract the two. But it's related with the on-shell action, if you want. But I don't think it will necessarily pick out anything to do with this length, but maybe it will. We haven't seen any evidence for that.
Well, do you know where this function is minimum?
As a function, well, we've showed you plots of that, right? This delta S that I was showing you, it tends to be minimal at the place where the two wormholes start showing up.
At the place where two wormholes start.
Yeah, so when we plot the delta S, it looked something like this, and so it's minimum here if you want.
Yeah. Okay, thanks. There's more to discuss. And one more thing, so maybe if you can say a little bit about this. So you introduce a spherical metric on the boundary of AdS spaces. Can you do this in some example, please? So for example, Euclidean AdS3 space has an
S2 at the boundary.
Yeah, exactly.
You
so
can
it's
do it.
The boundary of the hyperbolic space, but it's true topologically it is a sphere, but at least in mathematics, I've never seen an AdS space and you consider a positive curvature metric on the boundary.
You can do it very, very easily, right?
Well, you did it for us, so I believe that.
but you know, what's the problem with this? R squared over L squared plus 1 plus R squared. This is Euclidean AdS. What's the problem with that? This is a two-sphere. And you can check this is Euclidean AdS.
So how does the curvature -1 how do I see the -1 curvature here?
It's because there's this L squared here, there's a dependence on the radius here, and this is a positive number here. This translates into some negative curvature, which is then balanced partially by the positive curvature coming from here.
So
If it was the sitter,
somehow just in the first.
For instance, the sitter case would change this +1 to a -1 here.
Yeah, okay, that would change the curvature to positive. Okay.
Yeah.
George, for the gauge fields case, the U1 squared, you said you had to use some more intricate harmonic analysis on U2. Where does the U2 come in there in that example?
Okay, I'm gonna explain this to you. Thank you for the question. I actually love this. So this is sigma 1 squared. You understand that you can write the metric like this?
Yeah.
The round metric, right?
Mm-hmm.
So I took the case where A1 is equal to phi of R times sigma 1, and the other one times sigma 2, okay? So I preserve the rotational symmetry here, okay? And these things obey this algebra that I told you about, sigma 2 wedge sigma 3. Wait, sigma 3. So there's an SU2 algebra here, right? But there's still an enhanced by U1 here because I chose the sigma 1 equal to sigma 2. You see, I chose these two guys equal with an overall factor. And the U1
the
joins
A1
with the
is
SU2.
equal to A2, yeah.
Yeah, not equal to A2, but A1 is proportional to sigma 1.
Yeah.
And A2 is proportional to sigma 2 with the same coefficient. And so you preserve, like you can rotate the sigma 1 on the sigma 2. That gives you an extra U1. And the U1 combined with the SU2 to give you the AU2. Roughly.
I see.
And then you use some nice harmonics.
Oh, I see. The larger symmetry would have been SU2 times SU2. That's the symmetry of S3. And sort of
that's
reduced it to SU2 times U1.
Yeah, exactly.
I see.
There's a whole slew of literature on this. Bianchi type 7 universes fall in this class. And the harmonics on this are actually very useful if you're doing quantum mechanics. If I ever teach quantum mechanics again, I'll make sure that I'll talk about it. I'm sure the students are gonna.
Sorry, small technical question. So when you defined your wormhole geometry in your FLRW on search, you had this function which was the size of the sphere, right, as a function of the radius.
Yes.
Good. And you defined the wormhole as one where that function did not go to 0 at r equals 0.
Or anywhere, yeah.
Yeah, or somewhere, yes, that's right. And presumably you also had to put a condition on the derivative of this function with r, right, to make it smooth.
Yeah. And it's fine. You can do it.
Yeah, of course. Yeah, sorry. I was wondering, if we do not impose the condition on the derivative, is it easier to find, say, vacuum solutions?
If you don't impose the condition on the derivative, then
there would be like a massive brane there.
There's a certain sense where the boundary theory on the right will be different than the boundary theory on the left.
Right.
And then it's like they're coupling. And then it's easy to open wormholes, as Aaron Moll and others have told us.
Oh, I see. Thank you.
You double trace the formation will do it.
Okay, thank you.
So I think I can start hearing my children misbehaving downstairs.
Okay.
I hope it's okay, but I'll call it. We'll call it today. I would like to thank you, Raghu, so much for inviting me to speak here today. You were a great audience.
Thanks, George. Thanks a lot. It was a wonderful talk. I really enjoyed it.
Thanks.
Thanks.
Thanks, George.